Hello everyone, kia ora tātou, and thank you to the conference organisers for making this conference happen despite the tricky circumstances. I'm going to present the essence of a paper co-authored by myself, Min Hall, Hugh Morris and Graham North, which uses the process of writing earth standards for earth and straw construction in Aotearoa, New Zealand, as a way of discussing the challenges about regulating for low carbon materials. In order for more of these materials to be used, we need to be able to get them through the building consent process. We need rules. For the past 22 years, we have had these for many earth building techniques in the form of the New Zealand Earth Building Standards. And earlier this year, the revised and updated standards were published, and these now include more earthen techniques as well as appendices for straw bale and live earth methods. The three authors of this paper are members of the committee which drafted the standards, and you can read more about us here later if you so desire. I'm going to talk briefly about the history of earth building in Aotearoa, background to regulating low carbon materials, what's in the 2020 standards, research and testing done by members of the standards committee, and more importantly, the challenges of working within a changing regulatory environment, especially construction systems that do not fit into the mainstream. So some background. In the 19th century, settlers arriving from Europe, Australia and China brought earthen wall building techniques with them, including cob, sod, pisé or rammed earth and sun-dried brick or adobe. These were easily translated to the new environment, and consequently earth buildings became an integral part of the vernacular architecture of New Zealand, particularly in Te Waipunamu, the South Island. Moving into the 20th century, however, earth fell out of favour as processed timber became widely available, and it was much quicker to build a timber house. But after the Second World War, when there was a serious shortage of building materials, interest turned again to earth, not as a traditional material, but more as a modern building material. And this revival of interest was slowed down, unfortunately, when the supply of sawn timber came back on track. But in the 1970s, the global counterculture movement reached Aotearoa, and people became interested again in building with earth. And as this interest grew, so did the experience and expertise. And the Earth Building Association of New Zealand was formed in the 80s, and in 1998, the New Zealand Earth Building Standards were published. There were three separate standards: NZS 427, Engineering Design of Earth Buildings; 428, Materials and Workmanship for Earth Buildings; and 429, which is the earth building equivalent of the NZS 3604 for buildings not requiring specific design. If you were wanting to build a reasonably modest building using adobe, rammed earth or pressed earth blocks, then NZS 4299 was for you. All these houses have benefited from having those 1998 standards to guide the owners, the designers, the engineers and the building consent officers through all that is required to design, consent and construct a house out of earth. Now, in the year following the publication of the 1998 standards, 4297 and 4299 were cited by the forerunner of MB as a means of complying with clauses B1, B2, E2 and H1 of the New Zealand Building Code, that is for structure, for external moisture and for energy efficiency. Members of EBANS began planning for a revision in 2009, 11 years ago of the standards, and work began in earnest in 2011 with an unofficial committee, which included many of us who were on the original 1998 committee. But in the intervening years, government departments have changed, rules have changed, and Standards New Zealand, which was formerly a standalone agency with decades of institutional knowledge, has been whittled down to a tiny group of people working within the megalith government department that is MB. So this is the group of people who have worked for the last 4 years in an official capacity to get these standards over the line. It's been a long and exhausting process. But the revised standards are again the same three documents: 4297 for engineers, 4298 which concerns all earth construction and includes requirements for the raw materials and for testing. 4299 is for buildings not requiring specific engineering design, equivalent of 3604. But this time, it also includes sections on earth brick veneers. It covers single-storey buildings only, but also at the back of 4299, there are informative appendices on straw bales and light earth method as forms of construction. So these are the methods covered in the standards. There's 6 different types of earth construction. There's cob, adobe brick, rammed earth, also called pisé, soil cement, pressed bricks, and poured earth. And then there's the light earth and the straw bale. So I want to talk about testing. NZS 4298 covers the materials used and what to do with them. It goes from the general to the specific regarding the different methods. But there's also 16 tests ranging from assessing the clay content of soil samples through to strength testing, erosion testing, density tests, and more. And all of these are fairly low tech, meaning that they don't require laboratory testing. They can be carried out by builders and owner builders if they have access to reasonably simple gear. Take Appendix G, shown here in the diagram from the standard on the left. This includes a flexural tensile strength test, which can be constructed at home for testing sample bricks. These photos show a rig constructed by Alan Drayton of BioBuild and being used by Alan, myself, and Hugh Morris. We were testing the test prior to its inclusion in the standards. Testing has also been required for developments which have occurred during the last 22 years. If we look at 4299, which is the biggest, fattest standard, it sets out the process of designing simple earthen buildings on uncomplicated sites. And there are 2 particular developments which need mentioning. These are the increasing use of lower density earthen materials, which provide a much better thermal resistance value, and the use also of internal adobe veneer to provide thermal mass. This also, the internal veneer is also good at moderating the indoor air quality. Now, the particular lightweight bricks shown here have increased the R value to 1.5 as opposed to the standard heavyweight brick underneath, which has an R value of 1. And these lightweight bricks now satisfy Clause H1 of the Building Code for solid wall construction. And those thermal tests were taking place at Otago Polytechnic. As already mentioned, internal adobe veneer has become increasingly popular. Here are 2 examples in regular timber frame buildings. And with this increasing use of adobe veneer, testing became necessary to ascertain appropriate levels of fixing under seismic and wind loads. Hugh Morris led a team consisting of University of Auckland students, engineer Richard Walker, and earth brick manufacturer Verena Mader in conducting full-scale testing of veneer walls, and Nelson Evans also supported that testing. So a hinged concrete foundation was constructed, which allowed a large wall panel to be pulled over in a controlled manner by the digger you can see here, and then shaken around a fair bit. This testing provided the necessary evidence to formulate appropriate sizing for walls supporting veneers. These are included in the standard along with details for fixing, as you can see on the right here. This table, 12.1, is for the low density bricks. Table 12.2 relates to the heavier bricks. So to conclude, this paper set out to discuss issues surrounding the regulation of low carbon building materials using the review of the Earth Building Standards as a case study. Enabling owner builders and minimising material evaluation costs were key motivating factors for the committee members, who recognise that as well as offering a mitigating potential in terms of greenhouse gas emissions, low carbon materials are often also relatively low tech, making them innately suitable for use by beginners. Empowering those who wish to be involved in the construction of their own houses has obvious value when we're addressing the current nationwide housing shortage. Now, a really key requirement for standards development is financial support. Over the past 20 years, successive New Zealand governments have stepped away from active participation in rulemaking affecting the construction industry, focusing instead on process and oversight. This has meant that the ability to keep the regulatory system up to date relies heavily on industry funding. Such a situation isn't ideal even for mainstream materials such as steel and concrete and timber, but it seriously disadvantages most other low-carbon materials. For the low-carbon materials covered in the Earth Building Standards, it's been left up to individuals and organisations like EBANS to take responsibility for ensuring that they are updated. By the time Standards New Zealand became involved in the standards review, EBANS had spent $42,000 on developing them, and the expert volunteers had devoted thousands of unpaid hours. Thousands more hours were spent over the next 4 years. And in the end, a crowdfunding campaign was necessary to raise the funds to complete the process. So in order for these materials to be developed and used at the scale necessary to make a difference, we believe that there needs to be a concerted, internationally supported effort to lobby governments to provide support for research and experimentation, coupled with a commitment to a forward-looking regulatory environment that is not dependent on a very small industry. Regulations need to be regularly updated and expanded to respond to innovations based on practical experience, and they're essential to harnessing their potential as low-cost, low-impact housing solutions. Perseverance has just got the New Zealand standards over the line. We need to raise the profile, gain international support, and in parallel with others around the world, undertake coordinated local lobbying to achieve vital ongoing government support. Thank you.